Okay. Toussaint is in another room and Chaz not here. Okay, we are going to talk about the other optical instruments today. We talked about cameras last class period. So we will talk about first a simple magnifier, and yes, I have the doors open because of the gas from the last class period. Just try to let it get out of here. We'll talk about microscopes, and then we'll talk about telescopes. So these are, in addition to cameras, things that we like to use, multiple lenses to help us see things better. So first thing to talk about is angular magnification. We've talked about what is called transverse magnification. The magnification we learned before, the transverse magnification, was equal to the height of the image divided by the height of the object. And it turned out, because of the thin lens, geometric work, that was equal to minus the distance of the image divided by the distance to the object. What does the minus sign indicate? If you have a magnification that's negative, what does that mean? Not makes it smaller. Inverted. If the magnification is positive, it's upright, which means that the image is pointing the same direction as the object. That is compared to the principal axis. If the magnification is negative, that means that it's inverted. So the image is pointing the opposite direction as the object. So that was the transverse magnification. Now we're talking about a different magnification, the angular magnification. And the angular magnification is actually the one that's relevant to our eyes. Right? The transverse magnification is relevant to a projector. But to our eye seeing things, the angle that the object or image makes with our eyeball, that's what we see as the size. So if I stand here and I look at the screen is taller than my fingers outstretched fully away from me. But if I move back here, if I try to precede Toussaint to the back of the classroom, and I do the same thing, now my fingers are like twice as big as the screen. So that means the angle changes, just in that motion, it changed by about a factor of 2. It got twice as small or half as big when I moved to the back. And so when I'm looking at it with my eye, it looks smaller. Right? So the angular size, that's what's important to us, the angle it makes. And so for angular magnification, we'll define the angular magnification as the angle that it makes with our eyeball divided by the angle that it would have made alone. Now I say alone because we're usually saying I have my optical instrument and that's going to be the angle it makes with my eye when I look through the optical instrument. The words that the textbook uses are a little bit better. Angle aided divided by the angle unaided. So angle aided means when I'm using whatever my magnifier is. Angle unaided is I'm not using my magnifier, the angle it makes. So there are two different types of magnification. So it's important that you have in your head, these are different types of magnification. They both are magnifications. But one's talking about the angle, one's talking about the height. So let's look at how these things play. If I have an object like the stylus, and I want to see the nib on the stylus, if I hold it out here at arm's length, that nib is pretty small and I really can't see details, even though I can focus that far. So what can I do to see more details of that nib? I bring it closer. When I bring it closer, what have I done to the angular size? I've increased it. So I've magnified it. Now that's not magnifying with an optical instrument. That's just magnifying by where I place it. And so the biggest I can make this nib is going to be when I have it at the closest point where I can focus. What do we call the closest point I can focus on? The near point. So if I bring it at my near point, that is going to be the biggest angle that I can have for this object. So when we talk about a simple magnifier is like, I'm going to use this magnifying lens so I can see the details better. which, I mean, it works. Like, I can see the details better. I can easily see the pixels when I look through this. But I'm going to adjust things, you know, if I bring it as close as I can focus, that gives me the angle unaided. And then when I use this, I get the angle aided. So let's look at a simple magnifier as our first optical instrument. We're going to magnify the angular size. This has nothing new to us, so I'm going to move right past it. This has nothing new to us either. We're going to magnify the angular size by using a magnifier. So let's start with a question. What do you naturally do when you want to see something in greater detail? I've already, of course, gone through this, so this is just, you know, checking to see if you are in any way cognizant of what's going on. Okay, everybody that's here has answered. And everybody said, you move it closer to your eye. Good, that's what you naturally do. So now using a lens, oh, come on. I have way too many slides with words on them. Using a lens, I'm going to first do magnification so my eyeball is, well, allowing me to bring something closer to it and I still see it in focus. For a simple magnifier, you need to use a converging lens. How do you tell a converging lens from a diverging lens? The shape. If it's converging like this one, how can I just tell with my fingers that it's converging? Thicker in the middle, thinner at the edges. So this one, because it's thicker in the middle, it'll work for me. And I can use it as a monocle if I want to. When I use this, what it allows me to do is to bring something closer to my eye and focus on it. Like this, I can't focus. Like this, I can. And so it makes a bigger angle. Now let's go through the details of how we get the magnification with that. So we start with unaided vision. Unaided vision, the closest I can bring the object to my eyeball is, by definition, my eyeball's near point. Now, for our standard calculations, we will use n is equal to 25 centimeters. I know it's different for everybody, but to make life simple, we just use n equals 25 centimeters for the near point. So I have an object. What kind of object do I need to magnify? Big one or a small one? Small one, right? Big one, I don't need it to make bigger. So it's going to be a small one, which means that I can use small angle approximations. The small angle approximation is that sine theta is approximately equal to theta, cosine theta is approximately equal to 1, which means that tangent theta is approximately equal to theta. These are true if you're using radians. So if I look at my geometry, I bring my object of height h to the near point, and then I look, I have the opposite side is h, the adjacent side is n, so tangent theta is h over n. And if it's a small angle, then tangent theta is approximately theta. So I have here my unaided angle is h over n. What is h? The height of the object I'm looking at. N is the near point. So that's the biggest angle I can make with the unaided eye. Now I'm going to use a simple magnifier, and that simple magnifier allows me to bring it closer. And we're going to do this calculation two different ways. Way number one for unaccommodated vision. I hope I have the right number of C's and M's. What does it mean to be unaccommodated? It means you're staying at a hotel that's really not nice, right? No. Unaccommodated means that your lens is doing no extra work. It's relaxed so that you're focused at your far point. What's the ideal far point? Infinity. So unaccommodated means distance image is equal to minus infinity. Why a minus, by the way? Yeah, the image that's going to be made by this lens is going to be on the same side as the object. So that's why it's minus. So for unaccommodated viewing, my distance image is minus infinity. If I'm going to have the image at minus infinity, where's the object going to have to be? By definition, if the image is at minus infinity or plus infinity, then you have parallel rays and the object is at the focal point. You could also just say, well, 1 over f equals 1 over distance image plus 1 over distance object. 1 over distance image is 0, which means f is equal to distance object. And so you bring the object to the focal point, and the image is infinitely far away. So our image will be out at infinity like this. But this, what do we call this ray here that goes from the tip of my object through the center of the lens? We have a name for that ray. We had 3 different rays. Well, 4 if you were doing a mirror, but 3 for the lens. This is one of those 3. It starts with V. It's the V ray. So what is that point? What is this point here called? Not virtual. It's obviously V. Vertex. And so that's the vertex ray. What's special about the vertex ray? It goes undeviating. So my image out here also is going to be on that vertex ray. So the angle for the image is going to be the same as that angle from the vertex ray. So the angle that I'm going to see for the image is going to be this opposite side is h, the adjacent side is the focal length, or the opposite side is infinity and the adjacent side is infinity. Well, infinity over infinity is indeterminate. But because we know it's got the same ratio, we can say that our aided angle is the height over the focal length. The height is the height of the object. We don't know what that is necessarily. But what we do know is if I put these two together, the magnification is the angle aided by my instrument divided by the angle unaided. The angle aided, we just saw, was height of my object divided by the focal length, whereas the angle unaided was the height of the object divided by the near point. So we put those in, and this magnification, the angular magnification, is equal to the near point over the focal length of the lens. So that's the magnification you get with unaccommodated viewing with a simple magnifier. What's special about unaccommodated? I already said it, but what was special about it? Okay. The lens is relaxed. You have no eye strain. When you're using accommodated vision, you're having to use your eyes and there's eye strain. So we would prefer to use unaccommodated so that there's no eye strain. But if we do use accommodation, we can focus on things closer. So what's the closest distance we can focus on if we are using accommodation? Where should the image be located if we're using accommodated vision? It'll be at the near point. So distance image is going to be minus the near point. Why minus? Because it's on the same side. Right, so then we're going to have, and I have this picture on the next slide, but I think it's just better to go through and do the derivation. So I'm going to have my object here, my image here. This is the near point. And there's the angle aided. Well, how do I relate this angle to anything? How can I find that angle? Go ahead, say out loud. I still didn't hear. I probably should close the door. I hear Ken instead. Okay. So tangent of theta aided is going to be opposite over adjacent. So what can I use from that triangle for opposite over adjacent? H over DO. Well, DO isn't really going to help me. That's correct. That's what you needed to do. But it's not really going to help me because I don't know what the distance object is. What do I know? I know the distance image is equal to minus the near point. So let's use the thin lens equation. 1 over focal length is equal to 1 over distance object plus 1 over distance image. So solving that for 1 over distance object, so 1 over distance object is 1 over f minus 1 over negative n. And of course, we're all good enough mathematicians. What's the easier way to write minus 1 over minus n? Plus 1 over n. So I'm just going to write this as plus 1 over n. And I will substitute this for right there. So my theta aided is equal to h over f plus h over n. Now if I do the magnification, and I'm going to just go to the next slide because I have it on the next slide. If I do the magnification, oh, I don't have it on that. Okay, let's come back here. If I do the magnification then, I will have the magnification that's putting my theta unaided. Well, notice the h's everywhere cancel. And if I multiply top and bottom by n, this simplifies to n over f plus n over n. Of course, n over n is 1. So the accommodated magnification is n over f plus 1. What was the unaccommodated magnification? It was just n over f. So by straining the eyeball to its maximum, we increase the magnification by 1. Now if we are using a lens with a focal length of, let's say, 1 centimeter, that's a really short focal length. If I'm using a focal length of 1 centimeter, then n over f would be 25 centimeters over 1 centimeter, 25 times magnification. And if I strain, it goes from 25 to 26. We generally say it's not worth the eye strain to go from 25 to 26. And so we generally design our optical instruments and calculate our magnifications for unaccommodated viewing, for using the relaxed eyeball, because it doesn't make that big of a difference. And why strain your eyeball for really no payoff? That make sense? Okay, now we have the clicker question. As discussed, the object is placed at the focal point of the simple magnifier. Where is the image produced by the simple magnifier? That was for the unaccommodated viewing. Okay, everybody has answered. We had a grab bag here. Okay, this should not have had this much difficulty, so clearly I need to spend a little more time on it. But let's have you discuss it with your neighbors first to see if your neighbors can convince you of which way it should have gone, since they were pretty similar answers. Well,
I don't know, I was just thinking of that. Yeah. That'd be pretty funny. Yeah, can we take the sticker on this?
it's actually a cool idea. There are some people who put them on the walls. So you can...
Oh, that's cool. Okay.
We actually thought about that when we were building the building.
Oh, really? Huh.
Okay, let's try this again and see if discussion with your classmates helped you to come to a better understanding. Okay. Well, you'll be pleased to know that the number of correct answers stayed the same. So let us look at how we did that. How do you relate the image, object, and focal length distances? The thin lens equation. 1 over f equals 1 over distance object plus 1 over distance image. And so we set up here that we have the object is at the focal point. So we have f equals dO. So if I solve this for 1 over distance image, if f is equal to dO, I can just replace that to 1 over f minus 1 over f, or 0. And so if 1 over distance image is 0, what does that make distance image? Yeah, I know, it's a funny looking 0 because I started writing in infinity by accident. She said infinity, I knew I was getting to infinity, and yeah. Plus or minus infinity. Why plus or minus? It's going to be infinitely far away the parallel rays, and so you could go either way. And so there we have the two possible answers, plus or minus infinity. We look at these, and we had the focal point of the magnifier on the same side as the object. That would be the object, image, and focal point are all the same place. That was definitely wrong. Focal point of the magnifier on the opposite side of the object. Well, we saw that we didn't end up with 1 over f, so was not that. Infinitely far away, this is on the same side. That was one of the two options. And the last one, 2 focal lengths away on the same side, well, that was not one of the options. So you see how we got to the answer? Right? I mean, one thing I don't want is people like, well, I have to memorize this, I have to memorize that. It shouldn't be at all about memorization. It should be about understanding how it works. Okay, so here is where the work was finished out there for the magnification for a simple magnifier. that magnification was n over f plus 1 if you're using accommodated instead of unaccommodated vision. So, doing a simple problem. A converging lens with a focal length of 4 centimeters is used as a simple magnifier. The lens forms a virtual image at your near point. So which type are we using here? Accommodated or unaccommodated? Accommodated, because it's at the near point. Where should the object be placed, and what is the angle of magnification? This last one is actually, I made this assumption right at the beginning and never said it. We're assuming that you're bringing it as close to your eye so you get the biggest image possible. And so we're assuming that the lens is right beside your eyeball. Here it's specified just to make sure that we don't have any confusion, because yes, if you hold the lens out here, it's going to be a different magnification than if you hold it right next to your eye. And we're assuming you're holding it next to your eye. So how do we go about finding the answers here? We have focal length equals 4.00 centimeters. And the image is at the near point. Which variable did that tell me? Of distance image or distance object? Which one did it tell me? Distance image. And what was the distance image? Very close. Minus. And then it asks, where's the object? How do you find the object? Yeah. So we just say 1 over f equals 1 over distance image plus 1 over distance object. Therefore, 1 over distance object equals 1 over f minus 1 over distance image equals 1 over 4.00 centimeters minus 1 over minus 25.0 centimeters. We can actually do this one in our head because we're really smart. Common denominator is 100. And so this first one is 25 over 100. And the second one, minus and minus, is a plus, 4 over 100 equals 29, that's not a 2, 29 over 100 centimeters. So what is the object distance? Inverting that, 100 centimeters over 29, which is roughly, to two significant digits, 3.4 centimeters. Right, if that had been over 30, it would have been 3.3 repeating, so I just... Okay, so we were able to find that object distance. We can bring it all the way up to 3.4 centimeters away from the eyeball. Then the next question is, what is the angular magnification? It's what?
N over f plus 1.
Okay, we can just put n over f plus 1. Since we've already done all the theoretical work, we don't have to go back and reinvent it again. We can just say that's equal to 25.0 centimeters divided by 4.00 centimeters plus 1.
7.25.
So we have the magnification.
Can you just explain how you got it plus 1?
Okay, when your eyeball is focusing, so you're focusing on something as close as you can, which is at the near point, then we use the thin lens equation to find the 1 over distance object with 1 over f plus 1 over the near point. And then we used that magnification equation that it's the angle aided divided by angle unaided with that as 1 over distance object. Now, we had just found the distance object, so I could have gone through and done it that way. I could have said that my angle aided is equal to the height of the object over the distance object, and the angle unaided is equal to the height over the near point. And I could have just combined those two and said magnification and it'd give me exactly the same number.
Isn't the height, or aren't the heights different?
No, because both of those I used the object height. So that would have given me the same answer. But I went back to it with the derivation we had done. All right. Moving to a new topic. What is the point of a compound microscope? Why do we use these things? No, he's not here. That would be dishonest. Okay. 15, everybody. To magnify small objects that are nearby. That's correct. The point of a microscope is to take a small object that's close to you and make a bigger angle. The simple magnifier did the same thing, right? But the microscope should do a better job if it's going to be anything better than a simple magnifier. So let's look at how that microscope works. You have two lenses now instead of one. One lens we call the eyepiece because your eyeball, I'll make a big eyeball here, your eyeball goes right up to that eyepiece. The other one we call the objective because the object is near the objective, right? So it's named for what's next to it. The two lenses are going to do different jobs. The eyepiece is going to give you an angular magnification of the image produced by the first lens, by the objective. So the objective is going to give you a transverse magnification to make a bigger image. And then the eyepiece is going to magnify that image. So the magnification of the microscope is going to be the product of the transverse magnification produced by the objective and the angular magnification produced by the eyepiece. Now we've just gone through the angular magnification of the eyepiece. So the magnification for the eyepiece, I'm just going to use E for eyepiece, because if I use I, it sounds like I'm doing the entire eye, will be N over F if it's unaccommodated. We'll add 1 if it's accommodated. We generally go with the unaccommodated, so I just put that. That's the magnification you're going to get for the eyepiece. What about the transverse magnification for the objective? What was the equation for transverse magnification? Okay, we had height of image over height of the object, or minus distance image over distance object. And so I have the math on the next slide, so I'm going to go to the next slide. We're going to calculate this minus distance image over distance object portion. Okay, well, first slide was just restating the eyepiece. So I have minus distance image over distance object using the thin lens equation. I just solved that for 1 over distance object. And so this is what's inside that parenthesis. That's 1 over distance object that you had in the definition of magnification. But then I took that and I said, well, let's just bring the DI inside and factor out a focal length of the objective. So this here didn't have a focal length of the objective, right? This term here does not have focal length of the objective. So if I factor out 1 over focal length objective, I'm going to have to put a focal length objective up here on the top because there was nothing to factor out. And so that's where this focal length objective comes from. This distance image I brought inside, so I had distance image over the focal length objective that I factored out, minus distance image over distance image, that canceled out. And so this here is just rewriting by rearranging. That's all it is. But then the distance image, if you look at the picture, the distance image is going there to there. Well, the separation between the lenses, which we would generally consider the length of the microscope, is equal to the distance image plus the object distance for the eyepiece. But if we're using unaccommodated viewing, then we're putting the object at the focal point so the image is infinitely far away. And so distance object prime is focal length of the eyepiece if it's unaccommodated. Now this picture is actually showing for accommodated vision, but my calculation is for unaccommodated. So I'm going to write up here, I hit that thing twice. So for unaccommodated, the length is equal to distance image plus focal length of the eyepiece, which means the distance image is equal to length minus focal length of the eyepiece. So this here was substituted in right there. And so I have the magnification for the objective. This is the transverse magnification for the objective lens is minus, what does the minus mean?
Oh, it's flipped.
It's flipped, it's inverted. The length between the two lenses minus each focal length divided by the product, or divided by the focal length of the objective. And now I combine this to find the overall magnification. So the overall magnification is the product of the two, magnification of the objective times magnification of the eyepiece. So here's the objective magnification. There's the eyepiece magnification. And you put them together, and this here gives you the magnification for a microscope. Now our textbook just leaves it at magnification of the objective times magnification of the eyepiece, and leaves it to you to do all the work in between. But here we have it written out. What is that L?
The length of the microscope.
Defined as?
The length between the objective and eyepiece lenses.
Yes. You'll find some sources like the textbook I used last year that says, let's use the extra focal length and call that the length. That is the length from the focal point of the objective to the focal point of the eyepiece. That to me is confusing, but you can find different equations where they use a different definition for L. So it's important to know what these things mean and not just, oh, got an equation, let's use it. Now when you look at this, you'll notice that this is completely symmetrical between the focal length of the eyepiece and the focal length of the objective. Notice that? If you replace the E's with O's and the O's with E's, it's the same equation. That does not mean that a microscope works the same forward and backward. How many people have tried using something like a telescope or microscope and turn it around? It's not the same for a simple reason. The length is going to vary. Right? If you flip it around, you're going to have a different length that you have to make it to have it in focus, and that's going to change the magnification. So even though the equation is symmetric, the operation is not. You want to have the focal lengths both small, but the focal length of the objective here is the one that's really small, typically for a microscope. When you use a microscope, you can change the magnification. How do you change the magnification of a microscope? You switch the lenses. You typically have like 3 different lenses you can use down there at the bottom. Which one do we call the ones at the bottom? Objective, because they're next to the object. And you have different eyepieces you can put on. And the total magnification has to do with both of those lenses. Okay, one more thing on microscopes. The numerical aperture. The numerical aperture is a number telling you about the light gathering ability of the microscope. If that numerical aperture is small, that means you're not going to get much light. If it's big, you'll get more. It also relates to the resolution you're going to get, the best details you can see. The numerical aperture is simply defined as the index refraction of the material between your sample and your lens times sine of the half angle of collection. The angle of collection is shown as theta in the figure on your left, which you can just do geometrically. And alpha, it's not so clear. This picture comes from the textbook. Alpha is this angle right here. So alpha is just half of that full collection angle. So this is an important parameter you will see for your microscope objective lenses. The numerical aperture telling you about its collection. That's all I'm going to say about the numerical aperture. Let's move on to doing a microscope problem. A compound microscope, that's compound, it has two lenses, has an objective focal length of 1.4 centimeters, an eyepiece focal length of 2.20 centimeters. The objective and eyepiece are separated by 19.6 centimeters. What parameter does that tell me?
L.
Right. L is the separation. The final image is at infinity. What does it tell us if the final image is at infinity? That it's unaccommodating, which is the calculation that we did our equation for. So we have, what's the angle of magnification? Well, I can just use I hope I didn't forget the n on the previous slide. I don't think I did, but so that's equal to I ran out of space. I don't think you can see that I didn't choose a big enough area. And so you multiply that through, and what do I get for that magnification total? It's going to be negative. I know that much. Negative 29.9? I'm going to trust her and just go with negative 130. She's going to double check. She'll correct me if that's wrong. Notice the units. I have centimeters times centimeters on top, centimeters times centimeters on bottom. No units. 130. What does this mean that my magnification is 130 times? What's 130 times bigger?
The angle.
The angle. The angle that the eyeball sees. That's what's 130 times bigger. It's always important to remember when we talk about magnification what it actually means. That it's not, well, it's just a number. We have to learn these numbers. It doesn't mean anything to me. That it's not any use to you if it doesn't mean anything to you. Okay, what's the point of a telescope? We just finished microscopes. Done with them. What's the point of a telescope? We had 13 that said is to magnify large objects that are far away. Now, just to avoid any confusion, tele means far. What does micro mean? So a microscope is magnifying small objects. A telescope is magnifying far objects. And those far objects are by definition going to be large or we can't see them at all. And so that's why I put to magnify large objects that are far away. Right? You're not going to have an ant that's a mile away and magnify it with the telescope. No, you're not. Cassie's all, I can do it. So that's why I said large. It's making large things make a bigger angle with the eye. The first telescope I'm going to talk about is called a refracting telescope. That means it's made with lenses. Why do I talk about it first? Well, it's the simpler design. It's the first one that was created. Who invented telescopes? Trick question because you're going to get it wrong. Who invented telescopes? Who? What human is credited for inventing telescopes? The wrong one is the correct answer. She knows that I said you're going to get it wrong, so it's the wrong one. Usually people credit Galileo for inventing telescopes, but that's incorrect. We don't know who invented it, so I can't give the right answer, hence it's a tricky question. But we do know that it was invented by, well, people from Flanders, not the Ned Flanders. And Galileo heard about this thing that was being used as kind of like a cool, tricky thing. You go to a party, you look at this, and it's cool. And he was all, hey, I can use that for something actually scientific in nature. And so he went to try to buy one. The guys were already gone, but he got, people explaining to him, and then he started playing around, and he improved the design of the telescope. And Galileo was the first one to use the telescope for systematic scientific investigation. But he didn't invent it. The telescope has two lenses. Once again, there's the one closest to the eyeball that we call the eyepiece. And there's the one closest to the object that we call the objective. So far, it looks like a microscope, right? But the lens choice and how we're going to adjust it is different because we're going to adjust it for something that's very far. If something is really far away, where is the image going to be found? Go ahead, Sally. Well, if it's really far, then it's like the object is infinitely far away. So we have parallel rays, and where does that form an image? At the focal point. So these are going to come together at the focal point of the objective. That's supposed to be an O. Now, if we're going to have unaccommodated viewing, that is, the eyeball is relaxed, where's the image formed? From the eyepiece.
Farther away from the eye, right?
Farther away. How much farther away?
Enough they have to squint probably to see it. I don't know.
No, far enough that our eyeball is relaxed. How far is that?
Like 25?
Infinity. 25 is the closest. That's where we're straining the most. Okay. So we're going to have the image formed infinitely far away. But if the image is formed infinitely far away, where's the object going to have to be? Focal point. So not only is that first image going to be at the focal point of the objective, it's also going to be at the focal point of the eyepiece, so that we have parallel rays again. So the length is real simple. What's the length of a telescope? Well, they're different focal lengths. Yes, so the length is focal length of the objective plus focal length of the eyepiece. Now, this last part is tricky yet simple. And I'm going to go to the next slide where I have a picture for it. I think it's on the next slide. If not, then we'll skip forward until we get to it. Nope. Because the picture, a nice picture, makes it good. The object is infinitely far away. But that vertex ray will come here and make an angle that is equal to the unaided angle it would have made. And so our unaided angle, or the angle the objective sees, is going to be the height of the image it makes divided by the focal length of the objective. And of course, the eyepiece has the height of the image here divided by the focal length of the eyepiece for its angle. And so the magnification comes out to be actually really simple. You take the ratio of the angles that you would have seen aided to unaided. I made this myself, and I put this, I was consistently backward. It should be the angle of the eyepiece divided by the angle of that's seen by the objective. Everything I did here is exactly upside down. I am embarrassed, but at least I could correct it right away. So I end up with the magnification for the telescope is equal to minus the focal length of the objective divided by focal length of the eyepiece. Just by taking the ratio of those angles. So you want to have a really large focal length for the objective and a really short focal length for the eyepiece to get a big magnification. With telescopes, you change the magnification simply by changing the focal length of the eyepiece. Short focal length eyepiece, bigger magnification. Longer focal length, lower magnification. Okay, we're out of time, so we won't talk about the other kinds of telescopes today.